Tensors. I've been waiting a long time to do this video because tensors are vital. Tensors are vital in mathematics and physics. What is a tensor? Why do we need to know tensors? One of the most important theories in physics is Einstein's theory of general relativity. And in his theory, he expresses the equivalence between the flow of energy and mass on one side and the flow of the geometry of the gravitational force on the other. And to express these quantities, he needed tensors. And this is his equation. This is the Ricci tensor with two indices. The metric tensor with two indices. Metric tensor again, and the stress energy momentum tensor. But what is a tensor? A tensor is really not that difficult a concept, and we're going to go through it in a way so soon you'll understand it. The simplest thing to think about is to compare the differences between a scalar, a vector, and a tensor. A scalar, and a classic example is something like temperature or distance, is just a number. It's one physical quantity that you're representing. Now, for example, you could take a map of the Earth and you could plot at each point on the map of the Earth at a particular time, what is the temperature at that point on the Earth? And that would be one number. And it could be, for example, let's say right here in this room right now, it's 20 degrees Celsius. Now, that number and the way you plot it can vary depending on what coordinate system you use. Meaning, for example, I could plot the temperatures on the Earth using Fahrenheit, Celsius, Kelvin, etc. So I could say that the temperature right here is 20 degrees Celsius, or I could plot using Fahrenheit and say it's 68 degrees Fahrenheit. But the actual temperature has not changed. All that's changed is the coordinate system in which I'm mapping it. So if the coordinate system changes, and then the vectors or the basis vectors describing that coordinate system also change, so that if one part of the equation goes up, the basis vectors go down so that your final quantity is the same. So the temperature is going to be the same regardless of how I plot it, regardless of any coordinate transformation that I make. So that's why a scalar is considered a tensor. And the key aspect of this being a tensor is that it's invariant under coordinate transformation. So I can choose to plot it any which way I want, and it doesn't change the essence of what you're describing. So the key aspect, again, is that scalars, therefore, are a type of tensor, rank 0 in this case, because the rank of a tensor is the dimensionality of the array needed to describe it. And I'll explain that to you shortly. For a scalar, it's just one number. So it would be in the bracket, you would have one number, and that's it. That's a scalar. So what is a vector? Well, a vector is going to be different. I think we all remember what a vector is. A vector has a direction, and it has a length. The direction tells you the direction the vector is going in, and you could use any number of dimensions to specify that vector. It can be just in the x, or you can have a two-dimensional graph and you'd have to specify the x and the y, or a three-dimensional graph where you'd have to specify the x, y, and z, or you could have something where you need 4 dimensions, as Einstein did, the 3 spatial dimensions, x, y, and z, and time. But basically, once you describe a vector, you're describing an entity that has a direction, and it has a magnitude, and the magnitude is proportional to the length of the vector. Now, vectors, like scalars, and soon we'll see like tensors, are also invariant. Let's write it again, it's such an important word. Invariant under coordinate transformation, meaning that I can change my coordinate system, where you're in essence changing your basis vectors, and represent that vector in a different coordinate system, in which case your basis vectors, it's a little bit wet now, so in other words, your basis vectors change when your coordinate system changes. But the coefficients also change in an equal and opposite way. So even though you've changed your coordinate system, and so your basis vectors are different, and then when you plot it out, your results will look different. But when you combine the two back again, your vector has not changed. So a vector, just like a scalar, is invariant under coordinate transformation, and you can represent your vector in a different coordinate system and not lose any of the content. Nothing changes. You change your basis vectors one way, your coefficients change the other, the contravariant coefficients, if you will, and the two balance out, so nothing changes. So a vector is a type of tensor because it too is invariant under coordinate transformation. That's really the most important principle of all. So now, what is a tensor? Well, a vector is one quantity. A scalar is one quantity without direction. A vector is a magnitude and a direction. What's a tensor? A tensor is a relationship between two vectors. Now, a tensor can also represent relationships between scalars and between other tensors. That's a detail we won't go into now, but in the simple form, you can just think of a tensor as being a relationship between two vectors. So in this case, in order to describe the relationship between two vectors, then you're going to need a grid to describe that relationship. Because if you want to describe the relationship between a vector and a second vector, you're going to have to break down the components of this vector and break down the components of the second vector, and then your summary will be a grid where if you have x and y here and going down, and you have x and y here, then the relationship, we should put the x and y up here and the x and y down here. Then you're going to need to compare to fully describe the system. You're going to have to state what's the relationship between x and x, what's the relationship between x and y. Here, what's the relationship between y and x, and what's the relationship between y and y. So here now we have a rank 2 tensor because it's two-dimensional tensor. It's a actual two-dimensional thing. To fully describe the relationship between x and y in any one coordinate system, you form your tensor. And your tensor, because it's the relationship between those two vectors, that relationship between two vectors also will not change if you do a coordinate transformation. So because it's a relationship, just like scalars and just like vectors, you can do coordinate transformations of tensors and then end up with quantities that are invariant under coordinate transformation. So that's the important thing about a tensor, is that it's invariant under coordinate transformation. Now, tensors, just like vectors, are composed of your basis vectors and your coefficients. So, but they always change in a balanced way, so that once you represent your tensor in a certain base with certain basis vectors, you can change your basis vectors. And as long as you change the coefficients in an equal and opposite way, then the essence of the information, the relationship between those two vectors will not change. So a tensor is a relationship between vectors that does not change under coordinate transformation. So why is that important? Well, Einstein needed that in general relativity to express his theory, because if you look at this side here, the stress energy momentum tensor, the stress energy momentum tensor. What he is essentially doing there is breaking down the forces creating gravity into time and flow. So the four vectors, so basically you have your x, y, z, three spatial dimensions, but you add in a fourth dimension, time. So in Einstein's equations, it's a four-dimensional object with three spatial dimensions and time being your fourth variable. So again, so like I showed you before, if you want to totally map the flow or the changes in this system, you're going to have time, x, y, and z here. And then you're going to have time, x, y, and z here. So to totally describe the system, you're going to have to tell us how time compares with time. And that'll be an entry there. How time compares with x, entry there. Time and y, entry there. And time with z. And so on, x with t, blah, blah, blah. So because we're starting with a vector, with four different vectors in essence, the relationship between two vectors, each of four with four dimensions, is going to be a 4x4 grid. And that's why tensors are represented with these indices, which represents the rank of the tensor, because to describe that box, it's going to be T1, T1. Or to describe this box, it's going to be T1x. So you're going to need to, if these were all labeled like A, for example, this would be A0, A1, A2, A3. And this would be A0, A1, A2, A3. So the UV, when it's 1 and 1, it's representing this box. 1, 2 is representing this box. 1, 3, this box, and so on. So you need the index notation to represent all the separate entities in your grid. So when you compare vectors like this and get tensors, again, once you establish a tensor that's valid in any one coordinate system, it's going to be valid in all coordinate systems, even though you change the coordinate system, because the essence of the tensor does not change. It's invariant, again, under coordinate transformation. And that was the beauty of what then Einstein was able to do with his equation, because on this side, you have the stress energy momentum tensor, which, depending on which box you're working with, has units of joules, that's an energy term, per meter cubed. So joules per meter cubed is energy density. Joules per meter cubed is the same as newtons per meter squared. and same units, of course, they equal. And so this is the equivalence of pressure, right? And then this is a constant. And when you multiply out all the units in this constant, the units of this constant are 1 over Newton. So when you multiply, so we're taking this representation in this coordinate system, if you will, which is either joules or over meter cubed, or newtons over meter squared. Same thing, right? And then when we multiply by 1 over Newton, that is the proportionality of your coordinate transformation, if you will. And so if you multiply newtons over meter squared times 1 over Newton, you get 1 over meter squared. 1 over meter squared, you'll note, has just units of meters. In other words, it's a pure geometric representation. So you've done a coordinate transformation that gives you now on this side, and there's an equality sign there, of course. So now you have on this side the stress energy momentum tensor reflecting the amount of energy in a system and its flow through that system. And through a coordinate transformation now, you can represent it on the other side by a tensor or a group of tensors in this case, which through your coordinate transformation now represents the flux in this system in terms that are purely geometric. And that's why they like to say that gravity in Einstein's general theory is geometry, but actually it still is a force, but the force, it can be beautifully represented with a pure geometric representation of that force. So if we look again in a little bit more detail than at what we have on this side, because things have to match up. This is the Ricci tensor. The Ricci tensor was developed by Gregorio Ricci Curbastro. All his other papers, he called himself Ricci Curbastro, but for some reason in this paper that he wrote, he just called himself Ricci, and that's why it's called the Ricci tensor. It should be actually called the Ricci Curbastro tensor, but that's a minor point. The Ricci tensor is a contraction of the Riemann tensor, which is a more complex entity, but it can be summarized or contracted down to the Ricci tensor, which you notice has the same indices on this side as on this side, because two tensors to equal each other have to have the same indices and size. They have to be in the same units, obviously, and they have to have the same indices and size. So the units of the Ricci tensor are 1 over meter squared. Now, you subtract from this, when we get the equalities, you get minus 1/2 the Ricci scalar times the metric tensor. Now, the metric tensor is also a 4x4 grid. And it's basically a way of measuring distances and lengths when you switch coordinate systems. So any specific tensor, stress energy momentum tensor, will produce a metric tensor, G mu V. And we lose the Lanton coefficients because we're talking in 4 dimensions. So the Ricci scalar also has units of 1 over meter squared. The metric tensor, because it's I won't go into the details, but because it's the dot product between two vectors, will have a magnitude and no units. So the Ricci scalar as units of 1 over meter squared, times the metric tensor, which is dimensionless. So this component has units of 1 over meter squared. This has components of 1 over meter squared. And this beautiful term, minus, this is the cosmological constant. This beautiful term, Einstein added in his 1917 paper on his static spherical universe to explain why, if everything within a three-dimensional static object, if it all attracts, why wouldn't it implode? And he figured, my universe is not imploding. There must be some magical force, which he called the cosmological constant, that is basically a type of anti-gravity that keeps the universe from imploding. The units of the cosmological constant are also 1 over meter squared. The cosmological constant is a very tiny number. It's like 50 zeros and then a tiny number. And that's why it's so tiny that it only becomes significant when the metric tensor is very large, i.e. when we're considering very large chunks of the universe. So when we're considering our solar system or even our own Milky Way, these are the terms that are going to predominate and dictate how things flow. But as the metric gets larger and larger, then the cosmological term becomes more and more significant, such that when we get out to distances measured in millions of light years, not just 3 or 4 light years, but millions to billions of light years, then this factor, the dark energy, the cosmological constant times the metric tensor, is essentially your dark energy component. When the metric tensor is large enough, when you're considering big enough chunks of the universe, then the cosmological constant and the dark energy component predominates. And that's why at very, very large scales, all galaxies are moving apart from each other based on the Hubble rate. And the Hubble rate is essentially the rate that the universe is expanding. And the beauty that Hubble discovered was that the Hubble rate is directly proportional to the distance that a galaxy is away from us. The Hubble rate is approximately 75 kilometers per second per mega parsec. Now, a megaparsec is a unit of distance. 1 parsec is approximately equal to 3.2 light years. Okay. 1 light year is approximately equal to 10 to the 10th kilometers. That's 10 trillion kilometers. So 1 light year is 10 trillion kilometers. 1 megaparsec would be 1 million parsecs. So that would be like 10 to the 16th kilometers, which is a very large number, but it starts to add up. So in other words, a galaxy, if we measure a galaxy now and it's 1 megaparsec away, we can say, it's retreating from us at 75 kilometers per second. A galaxy that's 10 times further away is going to be retreating from us at 750 kilometers a second. If it's 1,000 times further away from us, it's going to be 7,500 kilometers per second. Interestingly, you'll see that the rate of the universal expansion is exponential. And at some point, you're going to reach galaxies that are literally receding away from us at faster than the speed of light. Not that because they're moving particularly fast, but simply because the space between us and them is increasing that fast. And since they're literally moving away from us at faster than the speed of light, their light can never reach us. That part of the universe is called the unobservable universe. We could wait an infinite amount of time for that light to get to us, and it never will, because right from the start, the galaxy is retreating from us at faster than light. So the unobservable universe is limited by this Hubble rate, and that's why it's called the Hubble horizon. And because of that, any universe, even if it is finite, will always appear infinite. But I've digressed. So let's just get back to tensors. The importance of tensors is that they are like scalars and like vectors. They're invariant under coordinate transformation. So once you establish a tensor that accurately describes the relationship between vectors, in Einstein's case, the relationship between x, y, z, and time, 3 spatial dimensions and time. Once you can describe that accurately in the form of a tensor relationship, then through coordinate transformation by multiplying by constants, you can generate something on the other side which captures all the information that you originally start, but maps it in ways that can be useful to you in order to predict what's going on. Because in essence, then, this is the matter in the universe and how it's moving. The matter in the universe and how it's moving then determines the shape of the geometry, or the net forces and how they're moving, essentially. And the net forces present in the universe will then dictate back to this side how the matter is going to move. So the matter dictates what the geometry is, and then the geometry will dictate how the matter moves within that. So it's like a feedback mechanism. And this equation, the general theory of equation, the general theory of relativity, I think is the most beautiful equation in all of physics, and one of the most brilliant revelations ever. And Einstein was a genius in coming up with it. The actual math involved is geometry, but you're differentiating. So it's not only difficult four-dimensional geometry, but it involves differentiation of this four-dimensional geometry, differential four-dimensional geometry. Yes, it's as complicated as it sounds, and that's why it took Einstein a full 10 years, once he had the idea, to learn the math sufficiently. And the type of math we're talking about is named after Bernard Riemann, who developed this math. And he wasn't thinking at all about gravity. It was just a purely mathematical description of geometry. He had no idea it would ever apply down the road to gravity. Similarly, some other brilliant people in the field, Tullio Levi-Civita, further modified Riemann geometry and simplified it. Tullio Levi-Civita, along with Gregorio Ricci Carbastro, which we all mentioned, and other brilliant guys and other principles we won't go into today. For example, Elwin Bruno Christoffel. He developed all these mathematical connections to Riemann calculus, differential calculus, that was vital for Einstein. So Einstein obviously did not work in a vacuum. I'm sure he would be the first to say that he stood on the shoulders of these great men, Riemann, Levi-Civita, Ricci Carbastro, and Christoffel, and developed this theory, the general theory, which has time and time again proved its worth by predicting ahead of time things like Schwarzschild used this equation and simplified it and predicted black holes before they were ever found. And gravitational lensing for example, was predicted by Einstein hundreds of years before it was found. Gravitational waves, interestingly, not really derived specifically from this. You have to go from the Riemann tensor and then use aspects of the Wheel or Weil tensor to sort out gravitational waves. But they too are essentially a prediction of the general theory, which literally took a century before we were able to build LIGO, which is the gravitational wave detector. The general theory, written in tensor format, tensors, like scalars, like vectors, are an important principle in physics. And you can't even begin to understand things like Einstein's general theory or other things in physics. For example, the relationship between electromagnetism and itself, or simply in engineering, the Cauchy stress tensor, which is a three-dimensional, looks at stresses and strains in a three-dimensional object, also a type of tensor. Tensors are essential in physics, and physics is what describes our world and our universe. Hope you enjoyed this. Don't forget to subscribe. I'll see you soon. I'm Romeo Bruni.